We present DR Live to explore, interpret, and diagnose RNN-based deep reinforcement learning models. DR Live contains 3 visualization views. The episode wheel allows users to efficiently overview a long game episode and identify interesting game segments for further detailed investigations. The projection wheel presents the high-dimensional data from 5 key data transformation stages of a DRL model using T-SNE projections. The dimension wheel helps users quickly identify dimensions of interest by sorting them based on metrics derived from all game steps, a single game step, and 2 subsets of steps. All 3 visualization wheels work together to identify dimensions or steps of interest. Focusing on them, users can perturb the DRL model and verify the functionality of internal RNN states. We now present how to explore game episodes with DR Live. Using the thresholding line from the episode wheel, we can easily filter out steps with low entropies. These steps are with the most confident actions issued by the agent. As shown in the projection wheel, most of them are fire actions, as reflected by the orange color. Zooming into one of these steps, we can check its game screen, action probability, and replay the surrounding steps. The step with the smallest entropy is where the ball hits the pedal, and the agent is very confident in issuing a fire action at this step. The good angle and speed of this bounce make the opposite fail to catch the ball, and the agent gets one reward eventually. Zooming into the blue cluster from the hidden states projections, we can investigate another playing strategy of the agent. By propagating the select step to the episode wheel, we saw the action taken in this step is no op, and the agent issued this action at the top corner of the wheel. Connecting the scattered point in the projection wheel into segments also helps to identify important steps. The starting point of a segment implies a sudden change in the data. Selecting a cluster of starting points in the hidden state projection, we can see an aggregated average screen in the game replay, showing the ball is always in the middle of the scene. Selecting one segment in the cluster allows us to see the aggregated variance map for the segment. Replaying steps around the starting step of this segment, we found the step is the start of a new game cycle as the ball just appeared in the game scene. Similar exploration can also be extended to the self-state projections. For example, for the currently selected cluster, the ball always appears in similar positions in the average map. Randomly select one segment to check the corresponding variance map and entropy curve. We find the starting steps of those segments are where the agent noticed the ball is coming towards him, and he becomes more careful when issuing actions as entropy curve starts to drop. More steps of interest can be found similarly. Next, we demonstrate how to identify critical RN state dimensions through different metrics. Sorting dimensions by the correlation with critical values, we found hidden state dimension 22 is a dimension that most positively correlated with the value curve. This dimension gets large positive values between every pair of Q short step and reward step. Steps in this range are very close to getting a reward, therefore their critical values are also large, making the two curves positively correlated. In contrast, the most negatively correlated dimension is 134. It shows large negative values between every pair of Q short and reward step. Sorting dimensions by the weight of critical values, we found dimension 185 has the largest positive weight. The hidden state value of this dimension becomes large at the reward steps, and it shows a big overlap with the reward curve. Multiplying the hidden state value with the large positive weight makes this dimension contribute significantly to the final critical values at the reward steps. Going to the self states and sorting the dimensions by their mean values, we identified the dimension 104, which works like a step counter and gets reset when the ball bounced up from the bottom floor in every game cycle. We can also identify critical dimension for a single step. For example, at step 1858, the agent confidently predicted a fire action. To find what dimensions have contributed significantly to this decision, we sort the policy weight channel corresponding to the fire action, which is WP1. Meanwhile, we sort the values of multiplying WP1 with the hidden state value of this step. The sorting shows dimension 57 contribute most positively to the final decision. The hidden state curve shows large values at this step, and the corresponding weight is the largest. The second most important dimension is 142, which shows very similar pattern with dimension 57. Dimension 164 is the third important dimension. Although the value of this dimension is negative at step 1858, multiplying its negative weight makes it contribute positively to the fire action. Dimension 216 can be analyzed similarly. Lastly, we identify dimensions through their dissimilar behavior in different subsets of steps. 3 metrics can be used to quantify steps' behaviors, which are their policy entropy, critical values, and step rewards. For example, we select 2 subsets with low and high entropy values. After the selection, the GSD between the 2 subsets are automatically computed, and we can sort the dimension using this metric. The dimension with large GSD values shows very different hidden state values in low entropy and high entropy steps, which plays an important role in controlling the agent behaviors. With the identified steps and dimensions of interest, we can interactively perturb the DRL model to interpret the internal RNN states. For example, checking saliency maps of steps where dimension 185 has large values, we found this dimension tracks the ball when it is on the left of the left pedal or on the right of the right pedal, which is an indicator of gaining or losing reward. There are 2 reward steps that this dimension did not catch. By interactively perturbing image pixels around the ball and sorting dimensions based on their sensitivity to the perturbation, we found other hidden state dimensions that work in complementary with dimension 185 to capture the reward steps. Focus on a specific step, we can sort dimensions based on the area size of the highlighted region from the salience maps to check what the important dimensions have captured. We choose one killshot step with low entropy and play the salience maps for 20 frames surrounding the step. From the animation, we can see dimension 32 tracks the ball before the killshot step. Dimension 46 stares at the right pedal to secure a good hitting angle and position. More interesting dimensions have been presented in our paper. Thanks for watching.